So what we have here is the Schrödinger equation for the rigid rotor, and that is described in this part of the PowerPoint. And we recognize that we have the Hamiltonian operator, and that is the operator for energy. We have the wave function, and that wave function y is a function of theta and a function of phi, and it's also including the quantum numbers of j and m. And also we see the same wave function on the right hand side as we're accustomed to seeing, and of course that means that we now have an eigenvalue in here for the energy, and we've seen that right from day one in this particular chapter. We also recognize that the Hamiltonian operator is now written in terms of spherical coordinates, and that's this expression that I'm underlying here. And that's a little bit more complicated than our Hamiltonian operator for Cartesian coordinates, and the homework was done to move from Cartesian coordinates to these spherical coordinates. But what I want to draw your attention to is that that Hamiltonian operator is the operator for energy, and it's equal to the angular momentum squared over 2 times the moment of inertia. But this is analogous to what we've seen before for the Hamiltonian operator for energy in terms of the linear momentum divided by 2 times the mass. So what we might also recognize here is that if we divide the Hamiltonian operator here, or if we cancel rather, if we multiply that Hamiltonian operator by 2 times I, okay, what we would end up getting would be this operator squared, the angular momentum operator squared, now simply in terms of an expression that I've drawn down the bottom here, where now you'll see that the 2i is removed from the bottom. And so the interesting thing now is actually if we were to remove, let's actually see if I can do this. Can't do this, but if I change the h hat for an l hat squared in here, and I remove the 2i term in here, then what we've got is a new eigenvalue, and the eigenvalue, let's remove the red lines already, the eigenvalue for the angular momentum squared is going to be this value here. So this is all a bit of a mess, so let's have a look at that in more detail on the next slide. And the point here is that we're going to find out that the spherical harmonics, remember the spherical harmonics are tied in with this, these are the spherical harmonics, that is this wave function y, and these spherical harmonics therefore must also be eigenfunctions of the operator for angular momentum squared. And so what we're going to learn from that is that the operator for energy, the Hamiltonian operator, and the square of the angular momentum operator, they commute. So let's have a look at that in the next section.